So let's again try to get the area of our circle using our new substitution method for double integral. Suppose you have your circle right here and I don't want to fill. So I have this circle and I know that this circle is the integration of 1 multiplied by dx and dy. And of course I want to integrate over this entire area. Now every point right here can be written in general as some x and some y. Those are called the Cartesian coordinates. We can also represent the same point using different coordinates. One of them, for example, is called the polar coordinate system. In the polar coordinate system, we represent every point as a radius from the origin, like that, so this is called r, and an angle like that from here to here. So every point P is equal to x and y in the Cartesian coordinate system and also is equal to some r and some theta in the polar coordinate system. Now this r is clearly the length of this segment, so r is really equal to the square root of x squared plus y squared. So this is the relation between r and x and y. Similarly, theta right here is really equal to tan minus 1 y over x, or tan theta is equal to y over x. So those are our transformation equations and we want to transform our integral in this new space. So I want to do this integral, and instead of dx dy I'll type dr d theta, but I know that this is not enough. I need to multiply by 1 over the determinant of the Jacobian matrix in order to make everything correct. Now if I want to cover all this area, I need to move r from 0 up to r and then move theta from 0 up to 2 pi. So this is my new limit of integration. Very well, now let's get this determinant of the Jacobian matrix. The Jacobian matrix is really equal to partial r by partial x, here partial r by partial y, here I have partial theta by partial x, and here I have partial theta by partial y. So this right here is the determinant of the Jacobian matrix. So let's get those results. So I need dr by dx and dr by dy. So r is equal to the square root of x squared plus y squared. Now dr by dx is really equal to 1 over 2 multiplied by square root of x squared plus y squared, here multiplied by 2x. So this is 2x. Now similarly, let's just remove that. Similarly, dr by dy will be equal to 2y multiplied by 2 square root of x squared plus y squared. Now the term right here is really equal to r itself, so this is equal to y over r, and similarly dr by dx is equal to x over r, and so dr by dy is equal to y over r. So very good. Now let's get this term d theta by dx and d theta by dy. So tan theta is equal to y over x. Now the derivative of tan theta is equal to sec squared theta. So I can say that sec squared theta d theta, if I deriving with respect to y, is equal to dy over x, right? So now d theta by dy is really equal to 1 over x sec squared theta. Now this is equal to cosine squared theta over x. Now let's get d theta by dx. So here I have tan theta is equal to y multiplied by x minus 1. So now I can say that sec squared theta d theta is equal to y multiplied by negative 1 multiplied by x power negative 2 multiplied by dx. So now d theta by dx is really equal to negative y over x squared multiplied by 1 over sec squared theta, but this is equal to negative y cosine square theta over x squared. So this is d theta by dx. Now let's create our determinant of the Jacobian matrix. Here I have dr by dx, which turned out to be equal to x over r. So here I have x over r. Here I have y over r. Here I have d theta by dx, which is negative y cosine squared theta over x squared. Here I have d theta by dy, which turned out to be cosine squared theta over x. Now let's get this determinant. I multiply this by this, so I'll get cosine squared theta over r plus this multiplied by this, so y squared cosine squared theta over x squared r. Very well, now I can get 1 over r as a common factor. Here cosine squared theta plus y squared over x squared, but I know that tan theta is equal to y over x, so this is tan squared theta. Also, tan squared is equal to sine squared over cosine squared, so sine squared theta over cosine squared theta multiplied by cosine squared theta right here. So this will give us cosine squared plus sine squared, which is equal to 1, and so this Jacobian is equal to 1 over r. Very well, now let's continue our integration. I wanted to do this integration right here, so I wanted this. Let's come here and let's paste this again. Now 1 over the determinant of the Jacobian is really equal to r, so this is equal to the same integral, but instead of this I have an r here, so I can multiply this r here, and this is my new integration after the transformation. This will give me here r squared over 2 and integrate theta from 0 to 2 by d theta. Now this will give me 2 by multiplied by this, and this will be again by r squared. Very well. Finally, I'd like to state that this will also work even if we have a function right here integrating. So we would be calculating volumes instead of areas. So if I have some other function, here the integration over some domain of x and y of f of x and y multiplied by dx and dy, and we want to use another set of variables u and v, then this can be equal to the integration over some other function of u and v after the transformation of du dv, as long as we multiply here by 1 over the determinant of the Jacobian. Also, I'd like to state that this will also work in higher dimensions. So suppose you are integrating another function in 3D. So I have 3 integration signs, and I have f of x and y and z, dx, dy, dz. And I want to transform to another set of variables u, v, and w. So u is a function of x, y, and z. V is a function of x and y and z. W is a function of x and y and z also. Then I can say that this integration is equal to another integration, another triple integration over some other function g of u, v, and w. Here I can have du, dv, dw, again multiplied by 1 over the determinant of the Jacobian relating all those variables, and in this case the Jacobian will be a 3 by 3 matrix, here having partial u by partial x, partial u by partial y, partial u by partial z here, and continue for the other 2 rows. Now there is one final very simple note right here. If I am performing double integration over dx dy, I said that this is equal to another double integration over du dv over multiplied by 1 over the determinant of the Jacobian. In my derivation, I assumed that the area right here was a rectangular area that got transformed into a parallelogram right here in the UD space. And we saw that dA1 over dA2 is really equal to 1 over the Jacobian right here. But if we look at this term right here, we might realize that this term is actually a rectangular area, not a parallelogram area, right? Because inside the UV space, I have something like that. So this is U, this is V, and this is DU, this is DV. So I have some rectangular area. The thing is, I have an area right here, right? So I have some area right here, and I have some corresponding area in the XY domain. And I want to partition this area into some parallelograms and get those areas, then multiply by the scaling factor to get the area of the corresponding rectangle right here. But I don't have to do this, right? Because this scaling factor will also apply even if I choose a rectangular area right here, du dv. In fact, this rectangular area right here will get mapped to a parallelogram area in the original space, but the scaling factor between this area and this area will still be the same. So what I'm doing right here is that I am partitioning this new area into very small rectangles in the UV space, and then for every very small rectangle I am multiplying this area by this Jacobian right here, or by 1 over the Jacobian determinant, to get the area of the corresponding parallelogram in the original XY space. And it really doesn't matter what space is rectangular and what space is parallelogramic, as long as we cover the whole areas by our summation of very small areas.